Okay, I'm going to be working 13.4, which is Green's theorem. So I'm going to start here with, I guess I'll go with number 3. So we've got, make sure I figure out where I can go to here. So for number 3, they give us line integral over the closed curve C of xy dx plus x squared dy, where C is the rectangle with vertices at 0, 0, 3, 0, 3, 1, and 0, 1. So here's our closed curve C. So we will we'll imagine here that we've got a curve C that goes around, positively oriented. It encloses the region here D. And by Green's theorem, if this is our P and this is our Q, then this should be able to be turned into the double integral over D of partial of Q with respect to Y minus partial P with respect to X with respect to area, which should be, since this is a type 1 region, actually this is a rectangular region, we can say our restrictions are X are between 0 and 3 and our Y is between 0 and 1. We can go 0 to 3, 0 to 1. Partial of Q with respect to X is 2X. Partial of P with respect to Y is just X, so minus X. And then dy dx, which is just integral 0 to 3, 0 to 1 of x dy dx. The antiderivative of x with respect to y is xy, evaluated from 0 to 1. And if we plug in 1, we get x. We plug in 0, we get 0. So integral from 0 to 3 of x dx, which is 1/2 x squared, evaluated from 0 to 3. I'm going quickly here, 9/2. I believe that's pretty straightforward. That's about as simple as it's going to get. 9/2. Okay, you know what? I think I accidentally just did number 2. I did number 2. Ah, it's okay. Well, that's a good example. Let's do number 3. I'll just change it to 3. So this will be x squared y cubed dy. And then our region is going to be the triangle with vertices 0, 0, 1, 0, and 1, 2. So here's our region D. We'll say our C curve goes like that. And I'm going to convert this to a double integral. So I just need to look at it as a type 1 region. So I need to figure out the equation of this line. This is y equals, let's see, y-intercept is 0, slope is 1, 2, 1, so 2x, and that's it. That's the equation. So my double integral is going to change over here. We're going to have partial of q with respect to x. Partial of q with respect to y is going to be 3x squared y squared minus partial p with respect to x, which is just y. And now my y is going to go from 0, which is here, up to this line, 2x. And then my x's go between 0 and 1. And then this is going to be dy dx. So the antiderivative of this with respect to y would be x squared y cubed minus 1/2 y squared, value weighted 0 to 2x, and that's y equals dx. And if I plug in 2x for y here, I'm going to get that this equals 2x into here will be 8x cubed times x squared is 8x to the 5th. And if I plug in 2x for y here, I get 4x squared, but then half of that, so minus 2x squared. And then when I plug in 0, it kills everything off, so just this. And now I'm going to do antiderivative, so 8/6 x to the 6th minus 2/3 x to the 30 evaluated 0 to 1, which would be, let's see, 8/6 is the same as 4/3 minus 1 in here, 2/3 minus, and then we plug in 0, we get 0, so you should just get 2/3. Now, the book asks you to do this in two ways. They want you to do it using the good old line integral and then compare that answer to Green's theorem. I'm not going to show you the line integral way. That's where you'd have to come up with parameterizations to go around this thing. And we'll get the same answer of 2/3. I'm just showing you how to apply Green's theorem. Do the other way on your own. All right, let's look at number 7. Number 7, we have line integral over c of y plus e to the root x dx plus 2x plus cosine of y squared dy. And our c is the boundary of the region enclosed by the parabolas y equals x squared. So y equals x squared looks like this. And x equals y squared, which looks like this. And so the region enclosed by both of those is the region in here. And what I'll do is I'll take this one and solve it for y. So y is equal to root x is this one. They hit each other here at 1, you can see. So what I'm doing is I'm going to look at this region in here as being D. I notice my x is bounded between 0 and 1, and then my y values are between these two functions. So my y value is between root x and x squared. And so I'm going to do my double integral. 0 to 1, root x to x squared, and then do, here's my q, here's my p. The partial of q with respect to x is just 2, nice, minus the partial of p with respect to y, which is just 1, isn't that nice, dy dx. So this is just 1. So the antiderivative of 1 with respect to y is just y, so we get integral 0 to 1 of y evaluated from y equals root x to y equals x squared dx. So I plug in first x squared, I get x squared. When I plug in this, I subtract root x. And I'm integrating that with respect to x. The antiderivative of that is equal to 1/3 x cubed minus 2/3 x to the 3 halves. So that's the antiderivative of this. 0 to 1. When I plug in 1, I get 1/3 minus 2/3 minus when I plug in 0, I get 0. So oh, shoot, I just noticed something. Oops. I got these backwards. My bad. This is real quick. Got the bottom one here was x squared. X squared root x. You probably noticed that and we're like, uh-oh. This is root x, this is x squared. All it does is changes when we plug in right here. This will be root x minus x squared, which when we come up here, it switches places, so this becomes the plus and the minus, and you'll get 1/3. I was just off by a sign, but it was because I had the limits of integration flipped over. Sorry, I'm trying to work quick. I don't have a lot of time and I'm kind of falling behind on these homework problems. All right, let's look at number 13. So they're giving us, they want us to evaluate this, and you're given that F is a two-dimensional vector field, y minus cosine y, and then x sine y, and it's the circle, it's x minus 3 squared plus y plus 4 squared equals 4 oriented clockwise. So x minus 3, 1, 2, 3, plus 4, 1, 2, 3, 4. So our center's here, our radius is 2. So 1, 2, 1, 2, something like this, oriented clockwise. All right, so our orientation here on 13, we're going to have, since we want to know this, right, we're going to actually look at the negative of that over the negative. So we're reversing the direction and looking negative. So remember, if this is C, if C is clockwise, to use the formula, we want to go counterclockwise, which is this. But in order to match it up, we have to put a negative out here. So if the C was counterclockwise, then we would just do this. But because we can only use the formula if it's positively oriented, which is the opposite direction, we have to say, okay, we're going to go the positive orientation, but we have to change the sign in order to match up the reversal of direction. So that FDR, which is equal to negative integral over negative C of P dx plus Q dy, where these are our P and our Q. Now, let's just go ahead and convert this into Green's theorem. This is equal to negative double integral over D of partial of Q with respect to X. So partial of this with respect to X is going to be sine Y. And then the partial, let me see if I got this right. Yeah, and then minus the partial of P with respect to Y. If we take the derivative of P with respect to Y, we get 1 minus derivative cosine Y is negative sine Y, so 1 plus, so minus 1 plus sine Y, and then dA. And notice here that the signs cancel, and you just get a negative 1. So negative double integral over D of negative 1 dA, but the negative can go on the outside, so this of 1 dA. So remember the property of double integrals, the double integral of 1 with respect to area over the region D is just the area of D, And so the area of this region D, we didn't even have to come up with any formula for it. The area of that is pi r squared. The radius of this circle, because of the 4 is 2, so times 2 squared, is going to be 4 pi. All right, let's look at number 17. Use Green's theorem to find the work done by the field. So they want us to find work done by the field F equals two-dimensional x times x plus y, and then xy squared. When we're moving a particle from the origin along the x-axis to 1, 0, the origin along the x-axis to the point 1, 0, and then along the line segment 0, 1, then along the line segment to 0, 1, which is here, and then back to the origin. So C is already positively oriented, which is nice. I already know I'm going to use Green's theorem, so I'm going to look at this. This has an equation, y equals negative x plus 1. I know my x's are stuck between 0 and 1. I know my y's are stuck between 0 and negative x plus 1. This is my p. This is my q here and here. This is x squared plus xy. This is equal to the integral over c of p dx plus q dy, which equals, if it's a positively oriented closed curve, then I can say that that's equal to the partial stuff. So partial of q with respect to y is 2xy minus partial of p with respect to x, which is going to be 2x plus y. 2x plus y. And then that's dA. So this is integral. I go 0 to 1. I go 0 to negative x plus 1. This is 2xy minus 2x minus y dy dx. Just before I move on, let me just double check that I'm got everything in order here. Which one is this? Partial of p, partial of q. Which one am I doing? 17. Okay, hold on a second. Did I write that down right? 17x, xy. Partial of q with respect to x. Robert, just having one of those days. Okay, partial of q with respect to x is partial of q with respect to x is y squared minus partial of p with respect to y. I should have wrote my darn formula down. Partial of p with respect to y is just going to be x. There we go. Oh my goodness. Okay, so now we go antiderivative of this with respect to y is 1/3 y cubed minus xy. Evaluating y equals 0 to y equals negative x plus 1 dx. Yeah, I changed that up there. I messed that up. Remember, Green's theorem looks like this. Partial q with respect to x minus partial p with respect to y. I did it the other way around. I did with respect to y with respect to x. Brain fart. Okay, so now we plug in here We get integral 0 to 1. Okay, when we plug in for y, we get 1/3 negative x plus 1 cubed minus x times negative x plus 1. That's what we get when we plug in this. When we plug in 0 for y, it's all gone. So this is it, dx, which, do I want to multiply that all out? We could. Well, you know, I think at this point it's trivial. It's all, this should work out to be negative 1/12. Okay, and then number 29, see if I can give you a hint on 29. I want you to think about 29. It's not a lot of work. I guess what I can say is this. So C is a simply closed path which does not pass through the origin. So C, simply closed path like this, does not enclose the origin. So we can imagine that you could enclose this with a region D, right? Right. So, or you could say that there's a D on the inside of this, right? Without any holes in it. I shouldn't have drawn that one on the outside. And so you just need to set up what that, since it doesn't have a hole in it, right? Automatically, just go calculate the partials and you'll see what the answer is. You'll be done. Okay, I hope that's enough. I know I went through that really quick.